Hi everyone, I'm David. You may have heard of overclocking or undervolting if you've ever built a PC. Did you know that these concepts can also be used in cyber attacks? Using some principles from circuits, an Arduino, and an oscilloscope, we're going to demonstrate a simple example of power glitching. So a quick outline of what we're going to see. We'll talk about the fundamental concepts behind these attacks, then we'll get into the specific setup. For the implementation, we'll talk about the target software before moving on to the hardware, and then we'll see the test results and ways to defend against this type of attack. In an introductory circuits class, it's common to assume that signals propagate through logic gates instantly. In the real world, this takes time, even though it's seemingly instant from an end-user perspective. The time it takes for a signal to propagate depends partly on the voltage. We can use higher voltage to force the signal through more quickly, but this increases power consumption and heat generation. In the case of clock cycles, one of the constraints on a faster clock is the time it takes for the signal to propagate. If we finish a clock cycle before the gates settle, we can end up in an undefined state. Conceptually, we're going to reduce the input voltage, which increases the signal propagation time. If we do this right, when the clock cycle turns over, the gates haven't settled, and we can skip some processor instructions. But does that really matter? Rather than walking through a bunch of Arduino code in a PowerPoint presentation, we're just going to hit the main points here. So the goal in this program is to prompt the user for a password and then enter an authenticated section of code if the password's correct. With a properly timed power glitch, we should be able to skip this password check and enter the authenticated section with an incorrect password. Our target system for this experiment is an Arduino Uno Rev 3. It's got a 16 megahertz advertised clock speed, but with this type of attack, we need to think about the margin built into the marketing metrics. We'll trigger the glitch using a Digilent Analog Discovery 2 board. This is a sort of multi-tool, and we'll use both the wave generator and the oscilloscope. It has a bunch of other stuff in it, like power supplies, a voltmeter, logic analyzer, and so on. Here we have a circuit diagram, so you don't have to look at a bunch of wires on my desk. On the left side, we have the Analog Discovery 2 board. The 1 plus and minus and 2 plus and minus blocks are the oscilloscope channels. T1 is the trigger, G and D is ground, and W is the waveform generator. On the other side of the diagram, we have the USB to TTL cable with broken out pins. The reason for this cable is so I can observe the serial monitor in the Arduino IDE and send commands. We can't use a typical USB connection without modification because it would supply power, and that makes it impossible to perform the glitch. Because we aren't dealing with your typical USB cable, we need to cross over the cables and map the TX to RX and RX to TX, respectively. For the analog discovery connections, the waveform generator provides 5 volts into the 5 volt port, and we also connect the ground for the analog discovery to the ground on the Arduino. The oscilloscope 1 channel monitors the serial connection so we can detect when the user inputs their password. Channel 2 monitors pin 12, and the reason is sort of a contrived way of finding when to trigger the glitch. In the code, we set pin 12 high right before the if statement where we check the password, and that helps us tune the glitch timing. Once the user enters their password, we need to skip the comparison instruction to enter the authenticated code section. Moving on to the waveform software of the Analog Discovery board, we've got a few instruments at our disposal, and this one is the wave generator. The Arduino runs on 5 volts as a baseline, so here we've set the offset value to 5 volts, and that's going to be our idle power supply. The amplitude, period, and frequency are all arbitrary values that we adjust during the tuning process. The type of wave we're going to generate is a burst pulse, so it's just a single square pulse, and then the length of the pulse is going to be half the duration of the period. We're set up to receive a trigger input from the T1 pin that we saw earlier in the circuit diagram. So when the oscilloscope reads that pin 12 goes high, that'll activate the trigger, and then that will, in the wave generator, trigger the pulse to drop the voltage before returning to the baseline power. The other instrument we're using is the oscilloscope, and just like the circuit diagram, we're using 2 channels. The yellow channel is one that we don't really need, but it's kind of nice to have. It's attached to the serial transmission line on the Arduino, so we can see after we've received the password input. The second channel is one we really care about, and that's attached to pin 12. So pin 12 goes high right before the password check, and it goes low after the password check if the password was incorrect. So we've set our trigger for the waveform generator at the rising edge for channel 2. So once we've exceeded 2.5 volts, then we send a trigger to the waveform generator to drop the power. If the power glitch was successful, then you'd probably see some fluctuations here on pin 12, but it would stay high because we would enter that infinite loop in the authenticated code section. If it drops, then we've bypassed that and we're back in the normal code loop where the access was denied. Fine-tuning the glitch was probably the most frustrating part, trying to dial in the parameters on the millivolt and microsecond level. I swept the pulse from 250 nanoseconds on the low end to 405 microseconds on the high end with no response. Longer pulse lengths than that triggered a reset, which should indicate that you're getting to the right range. From there, I kept trying to find the midpoint between having a reset and no effect, which should have eventually led me to the right glitch parameters where the behavior isn't well defined. The search was complicated by the fact that we're controlling two parameters, pulse length and voltage. The Along Discovery 2 board has a voltage resolution down to millivolts, but this test is operating closer to the maximum output of 5 volts, and therefore fine adjustments might be more challenging for the board. I think the biggest problem was the presence of a capacitor embedded in the Arduino board between the 5-volt pin and the ground. This smooths out the glitch and makes it more difficult to control the voltage received by the board precisely, and I suspect that's why the pulse lengths had to be so long to cause a reset. The reason for starting at 250 nanoseconds is because I expected that to cover just a couple of instructions at the normal Arduino clock speed. As I reached the boundary between causing a reset and having no effect, it became increasingly difficult to tune the parameters. Certain values would generate a reset sometimes but have no effect other times, possibly due to the whims of the capacitor. Because the capacitor is so small and integrated into the circuit board, it's non-trivial to remove and difficult to reliably short. I did try unsuccessfully to use a transistor for grounding the 5-volt input on the trigger to help discharge the capacitor more quickly. Before we move on, let's do a quick demonstration. Let's do a quick live demo to see how everything sort of works. Here we've got our waveforms application from Digilent, and on the right we've got the Arduino IDE. So everything's just as we described before. We're hooked up to the breadboard, and we've got our wave generator and our scope instruments ready to go. We're going to enable our channel. This will deliver power to the Arduino at the offset level, 5 volts baseline. Then we can see in the serial monitor we're connected to the Arduino. We've got our startup, and it's waiting for the password. We're going to start our scope. This way it's tracking and it's waiting for the trigger, even though it's not really showing anything right now. And then we're going to arm our wave generator. So this is switched to armed. We hit our run. We're going to trigger a pulse of, we're going to go from 5 volts to 2.6 volts for 812 microsecond period, so 406 microsecond pulse. And that's going to happen as soon as we enter an incorrect password. So we're just going to enter some garbage data, and then what we see here is that we've triggered a reset because the voltage dropped too low for too long. So we can change this to something smaller. We can drop from, say, 5 volts to 3 volts, so we get a little bit more power. And then we're going to arm the input again. And then as you can see here, we've ended up in, it just shows access denied rather than resetting. And the reason why I printed twice is because I accidentally left new line character at the end of the serial input as opposed to no line ending. That's the information you see. Trying to dial it in from here is getting exactly the right voltage and the right pulse length, which I wasn't able to do, partly thanks to that capacitor. There are several things that make power glitching more difficult. We need physical access to the hardware, and the timing has to be very precise, so we can't execute this kind of attack remotely. It can also require tampering with the hardware. If we have to remove capacitors, fuses, or the clock, then we may cause irreparable damage to the board. Sensitive equipment may also have anti-tamper features, which could damage other components unintentionally, or at least make it obvious that the device is insecure. Power conditioning is one way to prevent such an attack. As we saw, components like capacitors can even out fluctuations in the power supply and prevent brownouts. Multiple inputs and automatic switching can also prevent this type of glitch. We couldn't use a USB port on the Arduino to view the serial monitor because it provided a redundant power supply that would make the glitch impossible. Arduinos also have brownout detection, which isn't usually enabled by default, but can trigger a reset if the voltage drops below a specified value. Today, we talked about the concepts behind a power glitching attack. We had a simple sample program written for an Arduino, the hardware set up for an experiment, including the Arduino itself and the Digilent Analog Discovery 2 board. And lastly, we talked about the test results and the defenses against this sort of attack.